So the Chateliers principle says that a system in equilibrium will respond to stress in order to reestablish equilibrium. And so let's look at a generic example. Let's say that we have A plus B producing C plus D. And remember, this is a reversible reaction, so we'll have a double arrow here. And so let's say that let's say that all of these are aqueous in this case. Let's say that we are at equilibrium, and then we add more A to this system that's at equilibrium. If we add A to the system, we have debalanced it. We've unbalanced the system. It's no longer in equilibrium because it was in equilibrium, and we added components to it. And so remember, the equilibrium is that the rate of the forward reaction and the rate of the reverse reaction are equal to each other. And they're going to be equal at equilibrium because the concentrations of A and B moving in the forward direction equal the concentration in C, D. The concentrations determine the rate, not only concentration, but in this case, as we're looking at. If I add A, all of a sudden the concentration of A has increased. And we know that by increasing concentration, we increase the rate of a reaction. So if I add A, what has happened is I have increased the rate of the forward reaction. And by increasing the rate of the forward reaction, when I added A, we've upset the equilibrium. It is going to respond to that upset in equilibrium to rebalance itself. And so what's going to happen is A and B are going to be consumed and are going to make more C and D. And as A and B are consumed, the forward reaction is going to slow down and slow down. And as more C and D are produced, its reaction, which was this amount, is going to begin to speed up and speed up. And eventually, once again, just like any equilibrium is established, the rate of the forward and the rate of the reverse are going to once again be equal to each other, and we will have achieved a new equilibrium. And so in working with Le Chatelier's principle and equilibriums, we have to look at how the stressor is going to influence the system. And so one of those stressors is concentration. The concentration is going to change the rate of the forward or reverse reaction and therefore cause a stress, and the system's going to rebalance itself. And so if you add A, like we just talked about, if we add A, then the reaction will shift to the right. That's how we're going to term it. It shifts right. Because by adding A, we're going to increase the forward reaction until a new equilibrium is reached. So if we add A, we shift the reaction to the right. If we add C, the reaction will shift to the left. We're adding C, and the reaction is going to shift away from that stressor to try to rebalance it. You can also take away stuff. We could take away D. If we take away D, or remove D, if we take away D, then the concentrations on the right decrease, the reaction rate on the right slows down, and we're going to want to make more of it to speed that reaction rate back up. So if we take away D, then the reaction is going to shift to the right to reproduce the D that we took away. And so you can look at it in a couple of ways, but we look at it in terms of rebalancing the rates. If we add something, we're going to try to take it away to lower its concentration back down to what it was originally, although it's not going to be what it was originally. So if we add A, we're going to take A away. How does this reaction take A away? It takes A away by moving to the right. If we add C, we're going to try and take away C to rebalance it. It's going to take away C by combining it with D and turn it into AB. We'll shift the equation to the left. If I take away D, I need to replace D. Well, I replace D by having AB combine to make C and D. And so we'll shift the equilibrium to the right. Now, pressure is another thing that can influence the equilibrium of a reaction. In the case of pressure, what we need to look at is we need to look at gases. gas molecules, because those are the molecules involved in creating pressure. A solid doesn't create any kind of air pressure because the particles aren't free to collide with the surroundings. And so we look at gases for pressure. Once again, if we upset the balance, we're going to try to re-establish that balance. And so we have an equation, a reaction that's reversible, two-way reaction. And so let's say that we're at equilibrium, and then all of a sudden we add some more A. Well, that's going to shift it to the right. We already know that. But what happens if I increase the pressure? We don't add more of our gases, but we simply increase the pressure in this situation. So one way that we can increase pressure is by decreasing the volume. So let's say that we decreased the volume. We took our container and we made it smaller. If you do that, the gas is going to have less room to move around and the pressure is going to increase. And so let's say that we increase pressure. How does this system respond to that increase in the pressure in order to rebalance the equilibrium? And so what's going to happen here is we got to look at the gas particles. Gas particles create pressure. So on the left side of this reaction, we have two gas particles creating pressure. On the right side of the reaction, we have one gas particle creating pressure. And so if we increase the pressure, we want to relieve that pressure. The way that we relieve that pressure is we take two particles that make pressure and we convert them into one particle that makes pressure. If we have half the number of particles, we're going to have less pressure. And so this reaction will shift to the right as a result of a pressure increase in order to try to decrease the pressure, because we're taking multiple particles, turning them into one particle, which exerts less pressure in the container. If we decreased the pressure in this reaction, well, in that case, we would shift our equilibrium to the left, because if we decrease the pressure, then we're going to shift left, because that will re-increase the pressure, because we're making more particles, more gas particles are being created when we shift to the left. So we can decrease the pressure, and we will shift this to the left. Okay, shift it to the left. And that's how we will look at that. So when you look at pressures, add up the number of gas molecules on each side of the equation and shift accordingly. All right, let's look at how temperature affects equilibrium. And so we have, again, a generic reaction, 2A plus 1B making 2C reversible, so we need a double arrow here. And in this case, we have our enthalpy information. So we have a negative enthalpy. So this is an exothermic reaction. That's what our negative enthalpy means. And so I like to personally write plus heat. Heat's a product. So it's on the product side of the reaction because it's an exothermic. We're producing heat. If it were endothermic, positive, then the heat would be over here on the left side. We'd be adding heat to the reaction. All right, so if we look at temperature, well, what happens if I increase the temperature? Well, I'm adding heat, which is on the right side. So if I add heat on the right side, this reaction is going to attempt to shift away from that heat to take it away. And it's going to move to the left because we're going to consume that heat and move to the left. If I take my temperature and I drop my temperature, we make it colder, then the reaction is going to try to rebalance itself by creating some heat. And it's going to create that heat by shifting the equation to the right to produce some heat because heat's a product. And so in the case of changing the temperature of a reaction as it relates to the equilibrium, you have to look at what side of the equation is the heat. If it's exothermic, then heat is on the right side of the equation. If it's endothermic, then heat is on the left side of the equation. So in this case, by increasing temperature, we shift left. By decreasing temperature, we shift right. Now, an interesting thing that you can do with Le Chatelier's principle and temperatures and equilibriums is you can determine whether a reaction is exothermic or endothermic. And so here's some data. We have the value of equilibrium at different temperatures. And we can see that as the temperature is going up, the equilibrium is getting larger. And so by looking at your equilibrium expression, how does the value of Kc increase? Well, the value of Kc is only going to increase if the value of C, or the numerator, is going up and the value of the denominator is going down. And so that's the only way you're going to get Kc to increase, is C is up and AB is down. And so as the temperature is increasing, this reaction is shifting in a particular direction. Which way does this reaction shift? Does it shift left to right or right to left? Well, to make more C and less AB, this reaction must be shifting left to right. So as temperature goes up, the reaction is shifting right. Reaction shifts right. Now, what does that mean about where the heat is? Okay, remember the heat. Do we put heat over here on the left side, or do we put heat over here on the right side? Because as the temperature goes up, that's going to affect where the heat is. And so if the temperature is going up, we need to have heat on the left side, because the heat over here, of which as we add heat, it's going to try to get away from the heat. It's going to shift to the right to move away from the heat. And so this reaction happens to be an endothermic reaction because it consumes heat. As the temperature goes up, it consumes that heat and shifts the equilibrium to the right, and therefore the value of Kc is increasing. Now, last thing, what about catalysts? How does a catalyst influence the equilibrium? It doesn't. It doesn't influence. Well, it doesn't influence where equilibrium is. It influences how fast equilibrium is reached. A catalyst speeds up both the forward and the reverse reaction, and so it doesn't influence where equilibrium is. It simply makes equilibrium be reached faster. Now, that's not a bad thing. If you're producing something, you want to produce your product as rapidly as possible, because that means you can make more of it and you can sell more of it, and therefore your company can succeed. And so a catalyst is a useful product to produce more of your product that you want to do in a faster at a faster rate, at a faster clip. And so catalysts do not affect where equilibrium is, they just make you get to equilibrium faster. And the last thing for this one is, what affects the equilibrium constant, Kc? And the answer to that is only temperature. The only thing that affects Kc is temperature. Temperature, 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 temperature. That's the only thing that's going to affect the value of Kc is the temperature, because we have the temperature component to Le Chatelier's principle. Okay, that's it.